eigen. Incidentally, also the last eigen talk of the year. The year is wrapped up rather quickly and rather abruptly, it seems. But next weekend is Thanksgiving. After that, it's Dead Friday. And so, as far as eigen is concerned, we will see you again at the beginning of next semester. So we don't have very many announcements this week. One thing to take note, and I'm guessing you've probably seen some posters up for this, but tomorrow night at 7:30 there's going to be a showing of the movie The Imitation Game, which is a story, it's a slight fictionalization maybe of Alan Turing. Like I say, I've seen it. It's a wonderful movie. It's worth watching twice, in my opinion. So if you have the chance, definitely go see it. It's very interesting, very well done. Definitely worth going. That's at 7:30 in Newbold, correct? Newbold Auditorium, which is Buller Hall. So don't come to the Science Complex. Yeah. Honestly, a great place to watch. So, 7:30 tomorrow night, The Imitation Game in Newbold.
Any other announcements? All right. Well, our speaker today is Eric Siggy Scott, a graduate of Andrews University in 2011. He's currently pursuing his PhD at George Mason University. I believe he is studying algorithms as well as neurostimulation. So let's give him a hand.
All right. Good afternoon, everyone. I didn't realize that was the last talk of the year. If I'd known I was supposed to be the grand finale, I would have prepared a little harder. But, oh, this is the laser pointer, isn't it? I remember this. Okay. All right, so I see a lot of familiar faces that I'm happy to see, but to most of you, I'm a new face. I studied here in the computer science department, in the math department for majors, and physics department for minors. So I consider myself an eigen alumni as much as an Andrews alumni. And touch screen to log in. Proceed. Yeah, I turned it on like 20 minutes ago. Yeah. The next thing out of my mouth was going to be, so I'm a computer scientist, and then the computer failed.
It has to warm up now.
All right.
You got an hour and 2 hours.
I will trust you to finish working this out. So, I'm a computer scientist, and what I mean by that is not only that I majored in computer science, but I was so stuck with it that I decided to go on for a PhD. And what my first slide says that you can't see yet is, what is computer science? This is a question that I think is interesting, and from the moment you become a computer science major, you occasionally have friends and family members say, so what's computer science anyway? What makes it science? Aren't you just programming machines? And I think these questions, they're fun. There's no right answer. This is not something that a textbook or a course is going to teach you the answer to. But they're also important because I think it's helpful sometimes to reflect on the big picture of our field, my field, your field, whatever your field is, and ask, what is it we do and why do we do it? Because sometimes that helps you get the right direction in going with what you want to be pursuing with your work. So, one way of answering this question is computer science is the set of activities that computer science majors go on to do with their lives. So, I mean, you laugh, but that's actually a really, with these big fuzzy concepts, that's sometimes the best you can do. But what's it what?
What is recursion?
What is recursion? Some computer scientists go on to ask questions like that. So if we take that answer, computer science would be mostly engineering software systems, building the software that runs the machines in our factories and all sorts of things. Fun fact, the 97% of the CPUs in the world are actually little 8-bit things that are about as powerful as a PC in 1980, and your car has dozens of them. So code goes everywhere and permeates our society. But this view of computer science kind of lends itself to the idea that, well, computer science is really a branch of engineering. It's a kind of engineering, and that's what computing is. And that's okay. It's a perfectly sound definition. Lots of academics do research from this perspective, that we're helping software engineers do better engineering. But on the opposite extreme, Edsger Dijkstra, a famous computer scientist, and many other people have said that computer science is no more about the study of computers than astronomy is about telescopes. So this is it's kind of an extreme view, but it's getting at the idea that, well, computer science has something to tell us that's fundamental about the universe and the nature of reality, in the same way that mathematics and physics have deep natural things to tell us about the world. And there's truth in this. There's beautiful theoretical results in computer science that tell us big sweeping things about what a computer program is and what it can do, what it can't do. And it's really interesting stuff. But that is a very tiny slice of what computer scientists actually study. It's one field out of a multiplicity of fields. So I take a more middle-of-the-road approach between these two extremes. And I like to think that computer science is the study of well-defined problems and algorithmic procedures, so step-by-step methods to solve those problems. So this kind of combines both worlds. On the one hand, you have this huge, rich universe of mathematical objects, problems, and algorithms, which are essentially computer programs. And you can study any kind of these objects you want and call yourself a computer scientist. You can be attracted to beautiful things, elegant things, things that you think have big theoretical, philosophical, metaphysical implications. But at the same time, the fundamental object of our study, the same way a biologist studies various species out in nature, we study species of problems and ways to solve them. So at the end of the day, no matter how abstract we try and be, we're studying things that help us solve problems in the real world. So is computer science a science as science truly, or is it a branch of engineering? Well, I think it's kind of two sides of the same coin. We can't really escape either one in most computer science work that we do. So computer science becomes engineering research. And that means, usually, it means specializing in problems that don't necessarily occur every day, that don't necessarily impact the everyday behavior of programmers, though those are very important problems, but problems that are pretty tricky, and you need to have some scientific background, some capital to come in when you want to solve those problems. So like building a quadcopter. I've been watching these great YouTube, I've gotten into Arduino hobbyism lately, building little microcontroller electronic devices. And there are these great YouTube videos of people trying to build quadcopters from scratch and failing miserably. Because you can wire up the servo motors and the propellers, and you can make it lift off the ground, and then it immediately flips over, or kind of goes wah and crashes into your cat, you know. And that's because it's easy to build a quadcopter. Well, okay, I shouldn't say that. Mechanical engineers in the room will lynch me. But it's with some effort, you can build a robust quadcopter with materials and the kind of tools that a hobbyist would be interested in. But when it comes to controlling 4 propellers at once and trying to keep you level and straight up, that's a difficult control problem. And it's very hard to do if you don't have the right background in calculus, integration and differentiation, to build the right algorithm to be able to hold a quadcopter steady. So that's just one example, in meme form, of the way that a scientific approach lets you do something that you could not do before. So I live in the Washington, D.C. area now, and all the computer scientists there, pretty much, work for some government agency or other. Here's a picture of the Supreme Court. And our society is always setting these big, ambitious goals. And in the court's case, they like to talk about their constitutional obligations to release public records about about cases in a reasonable time, that justice delayed is justice denied, and things like that. And these big ambitious things that the government has to do sometimes hits up against problems that are very difficult for normal engineering practice to solve. And that's when computer scientists come in and say, well, here's an algorithm that I think could really improve your quality control process in your court records, or so on and so forth. And I think the reason I'm dwelling on this is I think that this whole idea of that science is giving us tools to address problems that are somewhat rare. We don't spend 100% of our time facing, quadcopter control problems. But that when we do face those problems, we need the background of science to help us get there. I think it's an important concept because the reason that we sit in our math classes especially, but classes in any field, and often as students have troubles connecting what we're learning to how it's important or how it can be applied. And the reason we occasionally find ourselves kind of snarkily asking our professors, do I really need to know this? Is because in an education, we are specifically learning things that will help us occasionally, but in very important ways. And I think even philosophy and religion plays that role many times. All right. So I said computer science is the study of tricky problems that come up that are important and that we need to solve them. There are a wide variety of problems in computer science that are actually really hard to solve. That no matter how big a computer you build and let it crank away, no matter literally, no matter how big you can imagine, Isaac Asimov turning a whole planet into a computer kind of thing, there are problems we cannot solve because it just takes too much computational effort to solve it perfectly. So computer science majors in the room will recognize that as your NP hard problems, theoretical classification. But there are other reasons problems can be hard too. They can be, from a more mathematical perspective, they can involve complex nonlinear dynamical systems, referring to it up here. So this is all the stuff that you didn't learn how to solve and study and analyze in differential equations class. This is all the stuff that we don't write closed form solutions for or even very many proofs about because we can't. We don't know how or it's impossible. So Dr. Henson's nodding. She's an expert in nonlinear dynamical systems and she knows how hard it can be to study some of these systems. And so what happens when you want to control one of these systems? What happens when you want to control a queue of airplanes at a large airport like O'Hare in Chicago? That even if we know exactly how fast every airplane takes off, I have a friend who's an operations research analyst, and he studies that. He studies how fast airplanes accelerate to take off and what that means for air traffic controllers. But no matter how much we know about the problem, there's going to be unexpected things that happen in a system that big and complicated. So some of my favorite examples here, protein folding. We know a lot about physics. We don't know everything about how atoms interact. But in a very real sense, we don't know how proteins fold into their shape. We know a lot about the mechanics of what attracts what and how the polymers twist and turn. But when it comes down to predicting exactly what form that protein is going to collapse into, and then how it's going to interact with another protein when it bumps into it and open up and grab it or whatever the magical things biology does, we're really bad at predicting it precisely. We can do it. I have colleagues that study this all the time, but they need really sophisticated algorithms that kind of work in ways that you might not expect. And finally, my favorite example of difficult problems, I met scientists this summer at a conference who are studying the problem that was featured in Gravity, the movie, where they're up in space and satellites start crashing into each other and blowing up, and the debris suddenly destroys everything that humans have put in orbit. And of course, in the movie, humans are in orbit too, and it's a disaster. That's actually a real threat, a real possibility. It's called Kessler syndrome catastrophe. And there are people in NASA that are like, what if something like this happens someday? Some accident causes a chain reaction. And what would we do? How do we prevent that? How do we get this space debris that will be in orbit forever around our planet to stop being in orbit? So I met some scientists this summer who study the question of, well, what if we launch a satellite into orbit that has some kind of arm or laser blaster? I mean, they used much more scientific terms in the introduction to their paper, but what if we built this little battle bot that we launch into space, and its job is to go track down all of the space debris we know is orbiting Earth and whack it, blast it so that it falls out of orbit, and we're cleaning up the environment in space to make it safer. That's actually a really hard problem if you want your robot to be visiting all the debris in space while all that debris is orbiting in these complex patterns, and you want it to knock it all down and not waste fuel, because it's really expensive to get fuel up there. So computer scientists in the room may recognize this as a variant of the traveling salesman problem, where instead of visiting all the cities in a 2D map, you are now visiting cities that are in orbit around Earth, and you have to visit them all in an efficient way.
That's sort of like Andrew's making a course schedule.
Yes. Yes, actually, you see this right here? Course scheduling is an NP-hard problem, theoretically. And at big universities, I don't know what our state-of-the-art is here. I know in the past there's been a lot of hectic committees arguing over how to resolve these problems. And even in scheduling employees in a business and stuff can be complicated. And companies build these big, sophisticated AI algorithms that can try and crank through that, but it's something you can't solve perfectly. So if you're having troubles, Dean Mattingly, you're not alone. It's actually a property of the universe that problem is hard. I'm not even kidding. This is one of our biologists have model organisms that they study, since they can't study every organism in detail. Computer scientists have model problems, and scheduling is one of our model problems to understand difficult things. So these are all problems that I've said are really hard, and I keep saying things like we can't really solve them. Now there's theoretical distinctions of what I mean by solve and what we mean by hard, but it's weird to talk like this because we do have algorithms that can solve these problems, at least reasonably well. We have to solve these problems, but the idea of an algorithm, which dates back to the golden age of Islamic science, where Hindu numerals and arithmetic was being introduced into the West, the idea of an algorithm is that I, as the algorithm designer, fully understand my problem. I have this great knowledge about the problem and how to solve it, and I'm going to delineate a set of steps that any novice in the market, as far as Muhammad ibn Musa al-Khwarizmi was concerned, or today, steps that are so easy that a computer could follow them, that then that algorithm can go and solve problems with the knowledge I imparted to it. But what do we do when we don't understand the problem? I just touched my mic. What do we do if we don't understand the problem well enough to really know how to solve it well? Because that happens a lot. So Lady Lovelace, the first computer programmer in history, emphasized that the computer they were trying to build only knew how to do what she told it to do. But to solve difficult problems, we have to move a little further, and we end up going in the direction of artificial intelligence, in a practical sense, not a iRobot take over the world kind of a sense. And we end up talking about algorithms, we're still talking about machines here, that can do things without being told precisely how, which is the exact opposite of the definition that I just threw up on the previous slide of what an algorithm is. What does it mean to make something that can do things without being told how when it's an algorithm? And this is kind of the basic paradox of artificial intelligence, is we're using a very dumb process, a computer, to try and build things that are, in some cases, smarter than we are, able to learn more about these really complex problems than we are. All right, so that is the 10,000-foot level philosophical background. For the rest of this talk, I'm going to talk about a class of algorithms that arguably has this property, that to some degree, they're able to figure out how to solve a problem that you, the algorithm designer, doesn't know how to solve. And so to get started on that, I'm going to confess to something I don't usually like to admit in public, and that is that I was a child once. And when I was 12, I lived in Nigeria for just a year, and one day, my father and I decided that we were going to go from the village that we lived in here in the foreground, and we wanted to go climb this mountain. After all, we were having an adventure in Africa, and white people in a foreign continent need to conquer things, so spoiler alert, we got to the top. The British had already built this little navigational monument. We weren't the first ones there, but So we hiked early in the morning, we got up before dawn, and by late afternoon we had climbed all the way to the tip top of this big mountain. This is a Google Earth image, but it's actually the same mountain. We got to the top of the mountain, and promptly 2 things happened. One, my father, who was here on top of a mountain miles away from the nearest person with his 12-year-old son, keeled over in pain with what we later found out was a gallbladder attack. And 2, the sun went down.
3 lions came out.
You know, on the way up the mountain, I didn't mean to go into this much detail, but on the way up the mountain, we went past a little cave area, and we were kind of climbing up an embankment, and my dad remarked, "Oh, I know what that smell is. This sounds just like the hyena cave at the Chicago Zoo." And boy, I climbed to the top of that embankment so fast. But, okay, so I have a problem. I'm 12 years old. I'm not particularly smart yet, or maybe ever. But now I am the leader because my father is in pain. He can kind of hobble. And the problem is get home to the village as quickly as possible. Now, there's a couple more things you need to know about the mountain. We're going to solve this problem together, like good computer scientists. And that is you can't really see it in the picture, but a lot of those little gray dots are actually little small cliffs and embankments and rocks that pose dead ends. And so it's not clear how to get down the mountain if you don't have a map. There is no trail because the locals don't see the point in climbing the mountain. That's not a practical activity. And one more thing, and here's a good thing, is as the sun is going down, behind us actually, we notice that the planet Venus rises in the east. And the village that we want to get home to just happens to be directly beneath the planet Venus. So, as long as we're headed towards Venus, we know we're headed towards home. But there's lots of obstacles in the way. And it's so dark that we have to use our walking sticks to see if there's a cliff that we're about to walk off of. All right, so this is a Sherlock Holmes exercise. You've got all the pieces. How are we going to solve this problem? What was that?
Build a quadricopter.
Build a quadricopter. So any ideas? So we're looking for strategies, problem-solving strategies that could help me get down. What would you do?
If you get to a cliff, it might be that it's not a far cliff. It might be a short cliff. You can see how steep the cliff
Okay.
is.
Okay.
It could be that it's just 3 feet and you could actually hop.
Right, so maybe investigate your local area
Yeah.
to see if there is a path. Put some effort into that.
Venus is going to move on. Like the stars are going to.
Yeah, it is. But we've got about 8 hours before it rises till you can't tell what direction for sure, arguably. Dana.
You have to do a lot of scouting because your dad can't backtrack.
There we go. There we go. Scouting. I liked her idea better than yours, Sam.
Dropping rocks. Actually, Sam, I'm just going to generalize your idea a little bit. I'm going to use this word, exploitation.
Yes. So your dad exploited you?
No, we exploited landscape to figure out how to get past the rough terrain. Okay.
Between the two of you.
Communication. Man, you guys went straight for the big principles. Okay, so how about what do I do when we hit a dead end? What do I do when we've tried to go towards Venus, but there's either a cliff high in front of me or a cliff low?
Backtrack to the last reasonable place.
Okay, backtrack.
Problem is dark. How do you know where you got to?
Remember where you went?
Just your follow the wall.
You can assume that you remember where you went, but that's in real life it's very difficult.
You need to keep record.
Yeah.
How likely are you to lose your father? Like, do you have a rope or something so you can be while you're exploring.
Let's assume that we have some kind of walkie-talkie, so we have a good communication mechanism. Because our algorithms don't generally lose each other when they solve problems.
If you go one direction, the next time you backtrack, you'll want to backtrack in the opposite. You know what I'm saying? You'll want to do a zigzag.
Kind of just switch back
Okay.
is what I'm
Yeah,
saying.
switch back.
Yeah.
Instead of just always backtracking and trying to the right and then trying to the right again, you're going to end up on the far right of the mountain.
Right, right.
There are multiple solutions, right?
Yeah,
That's
there's
like-
more than one.
Multiple paths down the mountain, if you think of the path as the solution. But if you think of planting your feet in the village, then there's one solution. So now, here's a question. I have another image of the mountain here from Google data. It's actually got a pretty complicated shape. What do you do if you end up having to go down a path where your view of Venus is occluded and you don't know which way the village is anymore?
How tall is you?
Are there shadows?
It's pitch black.
And how do you see Venus?
Venus is piercing through the shadows. See a hand?
Did you still have to track where you've been, like make a marker so you can see if you
Yeah?
go to another path?
Yeah.
you've been to?
You know, that's actually almost what we did at first, because my dad thought he couldn't walk, and so he tried to send me to get help, and he told me to leave markers and sticks pointing arrows of the path that I found down the mountain. I got 100 feet away. I'm like, this is not going to work. But okay, so here's what I was fishing for when I said, what if you can't see Venus? Go downhill. It's a pretty good heuristic. You're trying to get off the mountain, right? Right? And getting into the plains is the first step towards getting to the village. So since we're all mathematicians of varying degrees, I'm going to call that a gradient. Okay, so we've actually got all the pieces here of what I wanted to talk about, which is, and this goes back to this, is that if a mountain is shaped like this, and if your information about how to get towards your target is limited, so if you couldn't see Venus very well, or it rose in the sky and you weren't sure which way you were looking, then you can follow this greedy approach by exploiting your local environment and following a gradient. We started here, right? We knew which way to go to start, so we didn't go this way. Actually, we should have. Turns out there was a cattle path on the other side. But we didn't know that, right? We're working in uncertainty with a problem we don't understand. If we take what we call a greedy method, then we can quickly make a lot of progress until we get here, and then we don't really know what to do. And remember, this is a 3D surface, so we might have various dead ends here in the valley and stuff that we have to deal with. And some of you may recognize this from your calculus class. We're approaching the idea of optimization here, a local optimum. It's pretty easy to get to a local optimum if you're trying to get downhill. It's pretty hard to get to a global optimum if the problem is complex. So there are various strategies we can use, summed up in the idea of exploration. You can walk uphill sometimes, see what's over a ridge and so forth, to try and avoid getting stuck by going downhill and then saying, what do? I reached a dead end. Backtracking. What's that?
Find a stream.
Find a stream, there we go. See, that's an example of some real knowledge that you could bring in. If you know, oh, I know something about the world, streams flow downhill and they have to keep going. They can't stop. Then you can exploit that to find a quicker path. But a lot of the problems that we want to solve in the real world, we don't have knowledge like that. And it can be very difficult to come up with the specific information. So, this is the idea of search. And what I'm arguing to you, by using these fancy, more philosophical words rather than just talking about mountain climbing, is that search is a very general concept. That it's about more than finding that submarine that you can't find underwater in enemy territory. It's really about exploring a space of possible solutions to a problem. And this general idea becomes one candidate for the algorithm that gets us around Lady Lovelace's remarks about computers. That this becomes a general algorithm that can solve problems in a fairly general way without knowing in advance very much about the landscape that it's going to encounter. So what you need is a way of representing a candidate solution to your problem. That's usually easy to define something to do that. You define a space of solutions. And then you have to have a way of altering your solutions, a way of moving around in the solution space. And you have to know if one solution is better than another. You have to have some way of estimating if you're making progress. So these algorithms can play this game of getting hotter, getting hotter, getting hotter, getting hotter, getting colder, getting hotter, getting colder, getting hotter, getting hotter. Oh, it's this way, getting hotter. And in this incremental, haphazard, very ill-informed fashion, it can, especially with the use of teamwork, which we barely mentioned, especially with the use of teamwork and mini threads exploring the landscape, it can learn about the problem that it's trying to solve. And if you don't believe that this idea generalizes to more than mountains very well, I'm going to give you an example from a very different domain. So I alluded to this already. This is the traveling salesman problem. So again, this is think of it as collecting information about the problem landscape. It's trying to... Exactly. Yes, simulated annealing probably would have done that. It would have checked the other side. All of our methods for solving traveling salesman problems and related problems use a method something like this, a kind of random stochastic search that tries to avoid local optima. Now, they use much more sophisticated methods that do make use of everything that we do know about traveling salesman problems. Thank you. So the state-of-the-art algorithms use... I'll find my presentation. There we go. You use all the knowledge that humans do have to give the algorithm, but we can't tell it exactly what to do. It has to figure out some of it on its own. And Dean Mattingly, that's exactly how automatic course scheduling software works. It's the same principle. They just use a slightly different algorithm that tries to avoid visiting states that it's been to before. It's called taboo search. You try to stay away from places you've already explored. So what I've introduced you to is what today we call a metaheuristic algorithm. It's a general purpose search strategy that works in these abstract spaces of problem solving. And lots of different strategies that balance exploration and exploitation and communication in different ways have been proposed, most of them inspired by natural processes that adapt in nature. To learn about the problem that they're trying to solve while they're solving it. So at this point, this is sounding pretty good. I have told you now that there are algorithms that can figure out how to solve problems while they're solving them. Isn't that a neat trick? Even though at the base, the computer is still just doing a bunch of arithmetic really, really fast. You know, Al-Khwarizmi's old techniques. So this idea that there's a paradox between solving problems by rote and thinking about problems, it's a false paradox to a degree. And these algorithms have been applied to a huge variety of applications. Basically anywhere where we don't understand a problem well enough to design a really custom-tailored algorithm for that application, a metaheuristic algorithm can end up being useful. So this is from a recent survey of just applications of metaheuristics to car engine design. So you've got things like calibration of a control unit, optimizing the efficiency of a gasoline or a diesel engine, the shape of a crankshaft, all these things that engineers are pretty good at, but with the computer's help, they can solve these problems better. And there's so many of them that I couldn't even fit them on one slide. And this is just one field of engineering. It's not my field. I just thought this was a really excellent review paper. So that's the good news. But not surprisingly, building artificial intelligence is actually pretty hard. So let's not get ahead of ourselves. This whole field, in fact, all of artificial intelligence has been history of decade after decade of people being like, we found it. We found the tool that's going to solve everything. And then figuring out there are limitations to these tools. And the limitation here is we don't use these algorithms to solve problems like this with 3 nice little local optima. We use these to solve problems that often have hundreds of dimensions. You're exploring a 29 or a 300 or even just a 10-dimensional solution space, and you're looking for good regions and bad regions. And with high-dimensional systems, by the way, this is a point where something you learn about in your math classes may not seem important, but it is. You know, Calculus 3, you're learning how to generalize to higher dimensions. Higher dimensions are very important because in math we model a lot more than the 3 dimensions of physics. We model the 29 dimensions of a neural network, if that makes any sense at all. So in these high dimensional spaces, it takes exponentially more and more effort to explore the space. It's huge search space. You can never explore it all. You can never explore more than a tiny, tiny, tiny fraction of it. So you have to be really intelligent about how you explore. You have to find the stream and follow it down the mountain. You can't afford to scatter effort all across the mountain and so forth. So this kind of AI is all about studying the problem that you want to solve, making sure you understand everything you can about it, and once you get to the point where, okay, I really don't know what else to do, then you hand it over to the search algorithm. You try to make it as efficient as possible as you can. So really, while I described these algorithms in very glowing, optimistic terms, it's really this old dichotomy in artificial intelligence between what we call strong methods and weak methods. A weak method is very general purpose. You can chuck it at anything, and it will try its best to solve that problem. But it's going to perform pretty poorly on most problems because it doesn't have any a priori knowledge about that problem domain. Knowledge is very important in artificial intelligence. A strong method, meanwhile, knows a whole bunch about something very specific, and so it can solve that problem really well. But then you can't reuse that system to solve other problems. So this really is, there's a lot of manual engineering that goes into this. Applied AI looks actually a lot like the rest of computer science. We work really hard to understand our problems, design our algorithms carefully. So in the last section here, I want to give some ideas of what I believe is a philosophy that could bring us past some of these limitations that search algorithms have. So this is a picture from the surface of Pluto. I hope most of you have seen these pictures. It's fantastic. We just got to Pluto a few months ago. And on the one hand, this is a great example of a mountainous terrain that would probably be pretty hard to find your way around. So it's a hard problem in that sense. But Pluto is a really hard problem from the perspective of how the heck did humans send a machine there? When did we decide, you know what, I want to go to Pluto, and I'm going to make that happen. So I'm going to sit down and build a space probe and a rocket and a flight trajectory and everything that's going to be able to get there successfully. Well, we made that decision pretty recently, probably within all of our lifetimes. We did most of the decisions that went into this mission happen. But that's because we're at a place, right now, we're going to Pluto is easy. All the hard work of solving the problem of getting to Pluto has already been solved. Now, that's not to say anything disparaging about the incredible engineers that did so much work in novel science for this project. What it is saying, though, is that solving a problem as difficult as going to Pluto, you cannot solve problems like that by starting from scratch and saying, I want to go to Pluto. I'm going to drive towards Pluto. I'm going to dedicate my career towards Pluto. You need a lot more than that. In the case of Pluto, the journey started, you could go back thousands of years if you like, but there it is. But in 1790, somebody kind of accidentally discovered this thing called a vacuum tube while they were doing electronic experiments. And well, this was kind of weird, but it might be useful for things, so let's keep studying it. It fits a nice theoretical niche in the theory of electricity. And then a few more advances, the next thing you know, it made radio possible. And now electricity became the field of electronics, and all kinds of things started happening there. And then in 1947, the first transistor was possible, letting us do things more efficiently and in ways that were different than a vacuum tube let you do them. And the transistor was just the first. We recognized it was exciting. We're like, this is curious. We started studying it more. We built better transistors, smaller transistors. We got computers. The laser was discovered. Nobody had any idea what the heck we were going to do with a coherent beam of electrons. Nobody was thinking, let's make CD players when they set out to build the laser. So this whole idea in our culture that if you want to achieve great things, set a big, hairy, ambitious goal and then shoot at it with everything you've got. And if you don't have a specific goal, then you're a bad professional and you're kind of airheaded, is misguided in a sense. I mean, that works for realistic goals, goals that all the hard work's already been done, that the technology is already there. But it doesn't work for doing great things. The kinds of problems I've been talking to you about today are often the really difficult kinds of problems. We would like to be able to sit down and intellectually design an algorithm that solves the traveling salesman problem perfectly, but we can't. It's a very, very difficult task. And so I believe that the algorithms that we're designing to search these spaces need to do more than say, my goal is to get to the bottom, and I'm going to shoot for that. The idea of going towards Venus, the star, or of just going downhill and using exploration and so forth, assumes that by chasing Venus, that will provide you with the information you need to get to your destination. But on hard problems, that's just not true. Going towards your goal doesn't have you ever seen a Chinese finger trap? Where the goal is to get your fingers out, but to get them out, you have to push them in. That's a very simple version. I mean, I think all strategy games that we place in front of us on the table to entertain ourselves, like solitaire and stuff, are just mean. Because they're giving you problems on a small scale that actually belong to this NP-hard class of problems. And if they make them just a little bigger, even a computer can't solve it. Those puzzles are just mean because they're deceptive. That's a technical term in my field. It's a deceptive problem. If you try to solve it, it will lead you away from your solution instead of towards your solution. So I believe that what we need is algorithms that work more like human engineers. That instead of having one engineer trying to get to Pluto, we have 1,000 engineers trying to do 1,000 different things, like study this strange new thing called vacuum tubes. And through the process of an ecology of problem solving, we all share information, cross-disciplinary collaborations. I was talking this morning with Dr. Henson about the amazing things that happen when you get mathematicians from different sub-areas together and they suggest things to each other and they make breakthroughs that way sometimes. That's where the real engine of the hard problems comes from in our society. And so I believe that it's fruitful to ask how can we start to produce those same kinds of collaborations in computer science. And I'm out of time, so I'm not going to go into too much detail about that, but there's a little bit of exciting work that's starting to suggest that we can not get rid of, but we can avoid some of these problems in some cases if instead of going for one goal, we build algorithms that shoot for a bunch of goals at once that may seem distantly related. And the result is that the system becomes greater than the sum of its parts in the sense that it's now better at solving a number of different problems than it would have been if you tried for one of them at once. So that's the big idea, high-level talk of what I personally think computer science is, what I personally think it means to make a computer that can do things without being told precisely how. There's other ways, though. You know, most of what I talked about, we consider a subfield of, you may have heard of machine learning. It's a real big deal because it has all kinds of applications. The machine learning guys say, no. What you guys are doing is this weird off-the-beaten-path stuff. We don't acknowledge that. But we see ourselves as machine learning guys. So this is my take on machine learning. And finally, where I think that we can escape this hegemony of shooting for single objectives and try to build a system that can really be innovative, the way that we dream that artificial intelligence could be. And that's it. Time for questions. Archie.
Did you and your father make it off the mountain?
Yes. My father is alive and well. We did not spend the night on the mountain. We made it back to, what algorithm did we use? We used a combination of gradient descent, the heuristic of following Venus, and using sticks to see if cliffs were in front of us, and just trying to go around whatever we could. It turned out it wasn't that hard of a problem, but it was really scary. And we got there, they had sent out a search party for us to the wrong mountain. But everything was okay, and it's actually one of my most cherished memories for both my father and I. It's one of our most cherished memories of our adventures together.
The village used a multi-threaded approach.
I think they were actually all in one cluster, though. I mean, They only had 2 walkie-talkies. So. Philip.
Is there an algorithm for discovering if a problem is deceptive or not before you invest too much energy into trying to solve it?
There are lots and lots of algorithms that try and be smarter about this whole process that we kind of muddled through together, about instead of kind of randomly stepping up and down hills, of building a statistical model of the region around you while you're trying to solve it. So I don't know so much about methods that specifically try to say, is this being deceptive? Because that's really hard to detect. Basically means I have to know that the goal is someplace else and not where I'm being successful. But there are lots of methods for trying to be really statistically smart about understanding what the landscape is doing to you and what the landscape is telling you.
But you can tell how a deceptive thing behaves, and so once you start detecting that it's behaving that way, then maybe you found an algorithm for that.
Yes, yes, and you're getting towards one of the major intuitions that's really driving the field right now, is this idea that you can compute statistical properties of a problem with a relatively small amount of computational effort, just take some samples, and that maybe that will tell you something about what search strategy you should use, or what other things you should do to solve the problem. This whole idea of trying to be able to identify a problem that's something like something you've seen before, and be like, oh, I should use this technique because this vaguely looks like this. A more sophisticated version of recognizing, that streams should take you downhill.
Well, that's all the time we have for right now, but let's give Siggy another hand. And if you have any more questions for him at 2 o'clock in HYH 321 on the 3rd floor, there will be an Ask Me Anything type event with Siggy, and the Coding Club will be providing free pizza, so be sure to pay him a visit then.
What time is that?
2 o'clock.
I feel like you said directly.
30 minutes.
So I think you would know best.
Pretty much as soon as he starts.
So we don't have to wait half an hour, is what you're saying? All right, all right.
We just bomb hard, we can questions.
All right, then let's get pizza.